So let's start with a scheduling example as a vehicle to demonstrate greedy algorithms. So we're given jobs, J1 to Jn. Think about those jobs as each jobs require a certain time that is given to you, Pi, right? So Ji requires Pi time to complete. Think about Pi as, I don't know, in seconds, if you're thinking about it as a computer that has to run those jobs. And the question now is how you should schedule those jobs, right? The question is, what are you trying to optimize, of course? So here what we are trying to optimize is the total waiting time or the average total waiting time. So what do we mean by that? If we schedule them, so look on this example. This is how much time each job takes, and let's assume they schedule them in this order, right? So the first job is going to take, the first job is going to take 3 units, right? Okay, so let's see. J1, it's going to be 0, right? Because it's the waiting time before the job got started scheduled, right? That's what you're waiting, right? Once you're processed, you're processed. So for the first job, it's going to be 0. This is it. For the second job, it's going to be this, right? 3, because you're waiting the 3 unit years. The third job is going to be 3 plus 4, because you're waiting the waiting time of the first 2 jobs, and so on, right? For every job, the ith job that you decide to schedule, you have to pay the total time it takes to process all the previous jobs, right? That's the name of the game. Okay, so that's what we want to optimize. And the optimal schedule, of course, is what, right? How do we come up with the optimal schedule? So the intuition is, think about an example where you have a lot of tiny jobs that are of the same length, and then you have one monstrous job, right? By the way, anytime you try to solve a problem like that, it's best to first think about some special case to get some intuition about what's going on. Okay, so we have this, right? And now one option is to schedule the big job first and then all the tiny jobs. Or the other option is to schedule all the tiny jobs first. Since they're the same, it really doesn't matter how you schedule, and then the big job, right? That's kind of the 2 possibilities. And clearly here, the second option of scheduling the short job first is more natural, right? Because, the big job have to wait a long time, but it's a big job, so that's fine. And that's also what would happen in life, right? If you show up in a store and you want something to get fixed and you have a tiny thing, you would be handled before somebody that needs a major amount of work, right? So as such, the optimal strategy turns out to just schedule the job by their processing time, increasing order, and schedule them according to this order. So this is shortest job first, SJF. Okay. So the claim is that this shortest job first gives optimal schedule, minimizing the total waiting time. Okay, so the basic strategy is going to be an exchange argument, where we are going to show that if we have 2 jobs where the bigger job is scheduled first, then we will benefit from exchanging them. Okay, so for the proof purposes, let's assume that the input is given to us already sorted, namely the first job is smaller than the second job and third job and so on in processing time. And now all you need to do is to really look on a schedule. So let's assume that we have 2 jobs, in this case the blue job and the green jobs, where the blue job is longer but it's scheduled earlier, right? And what do we have to pay? Well, we have to pay, well, it's not drawn here, but 0 plus, and so on, right? We have to pay all the blue, sorry, all the green interval, all the blue intervals, sorry. So now let's think what happens if I exchange those two jobs, right? Which are wrong, right? They have inversion. So what happened? All the intervals are the same, except that this interval, this portion here, got shorter, right? So clearly it's better. And that's all you need to argue, right? So the idea is that if there is an inversion, in the optimal schedule, you can inverse it and get a better schedule that has lower total completion time, total waiting time, which means that the optimal schedule is increasing in order. So that's it. But proving it formally requires a bit of work. So an inversion is if we look on the current schedule we have, and we have a job PA and PB. Oops, let me call it PB. Such that this one, PA, is longer than this one, right? So this is called an inversion. Right, okay. But what we want for the argument before is to argue that if there is an inversion, then there are two consecutive intervals that are inverted, right? But this is not very hard to see, right? So how would we see it? Think about the length of the job as P1, P2, Pn. I know that PA is bigger than PB, which comes after it, right? So you can think about this as an interval of numbers. And if those PA and PB are next to each other, then we got this adjacent inversion as we wanted. If not, you can pick any number in the middle, PM, right? Now there are two possibilities. Either PM is larger than PB, and then you continue the search in this interval. This is just the logic behind binary search. Or alternatively, PB is PM is smaller than PB, but if it's smaller than PB, then it's definitely smaller than PA, right? Because PA was bigger. So then you continue the search on this interval, right? So it's essentially just a binary search logic. And since binary search shrink the search of interval, and we begin with an interval that have at most a number after, a finite number of steps, we will get to two adjusted number and the claim would follow. So this is the easy proof of this. So we have adjacent inversion, and now we are done, right? Because assume that we are given, we're still in the proof, right? That SJF is optimal. So assume you have the optimal schedule and it's JY to JN. And it's the optimal schedule that have minimum number of inversion. So if it has no inversion in the optimal schedule, then SJF, it means that it's sorted in increasing order, and SJF and the optimal solution are the same. Otherwise, there is an inversion, but we just argue that if there is an inversion, there is an inversion of two adjacent numbers. And if there is an inversion of two adjacent numbers, we just argued that if we exchange it, the price goes down, right? So, right? And now we are done. So we got a contradiction because we started with the optimal schedule and we got a schedule that has better total waiting time, which is of course impossible. So it must be that indeed the optimal schedule is sorted exactly like the optimal algorithm. Okay, let's consider the weighted version. Unfortunately, I wrote it in the wrong way. So now every job has a weight, So for every job there is a weight. Think about it as price. We are in the schedule person model, right? So there's not right? And now we want to minimize the total waiting time. So I wrote the function here, but what I wrote is not quite true. So let's try again, right? We want to find the ordering. So let's go, we have an ordering pi, right? We want to compute the permutation pi. 1 go to n, j go to, let's see, 1 to I minus 1, right? Of p pi j. This is the total processing time of all the job before the I job. And that's what the I job has to pay, right? So this is what we are trying to minimize, this price function, right? So given this price function, okay, compute the optimal schedule, right? So the additional thing is that now we have weight, right? Think about weight as how much you're being paid for the job in some sense. And the intuition is that if somebody pays more, they should be scheduled earlier, even if their job is larger, okay? So think about how to solve it. I'm going to solve it next, but think about it before moving on to seeing the solution, okay? This is it for now.